Hello everyone, welcome to the lab. In my previous video I repaired and tested this amplifier, and some people wanted to see more testing done, in particular some characterizations such as frequency response and maybe total harmonic distortion, which is THD. So let's talk about that. If you watch my channel, you probably know that I am interested in all sorts of measurements and characterizations, and even in some precision stuff like metrology kind of thing. So I decided to do some more measurements here and show some techniques I'm using. There are so many ways, depending on how thoroughly you want to characterize a device under test, and on your budget and goals and such. First, let's do something quick and easy using my Keysight InfiniVision oscilloscope with built-in signal generator. I'm going to use a dummy load, which is this 8 ohms 50 watts resistor, and I have this BNC to RC adapter to connect the signal generator. Let's go. The dummy load is connected to the left channel, the oscilloscope probe is across the dummy load, and the generator is connected to the left channel as well using CD input. So let's turn on this function generator, and now if we turn up the volume we should see some output. Let's say around 10 volts peak to peak when the volume knob is slightly above 10 o'clock. So now we should be able to look at f of t, and I already adjusted the range here, so the span is 20 kHz and center is 10 kHz. We are looking at the range from 0 to 20 kHz. And we can adjust the horizontal scale to have more resolution, like so. And we can disable this channel 1 waveform. And let's turn the volume down a little to see the fundamental all the way. Something like that. So we see a fundamental tone and some harmonics. And some viewers suggested that we can measure THD this way. Can we? Not really. Two big reasons. The first one is that this source is not nearly clean enough for the purpose. The THD of this amplifier is about 0.03%, and that's the worst case, so we should be prepared to measure below that, let's say 0.01%. And the THD of this function generator is about 1%, so it is not nearly enough for the purpose. We need a much cleaner source for this THD measurement. And the second reason is that the resolution of the front end here is only 8 bits, and most oscilloscopes are like that, and that is also not enough for the purpose. So THD is out of question. And how can we look at the frequency response? One way would be to sweep across this range and enable some sort of max hold or persistence. But unfortunately, this built-in generator does not have a sweep capability, except a special case, and I'll get to that later. So what we can do for now is enable a noise source instead of a sine wave. And now, if I turn up the volume, we can see that the noise floor goes up. And that's because the source is a white noise, which means approximately equal energy at all frequencies. So now the shape of this top is our frequency response. And because the tone controls are in the middle, we expect a flat frequency response, and it is approximately flat. Now let's try boosting low end, and here it is. And it only affects that small region here because unfortunately this is not a logarithmic scale as it should be for audio analysis. So let's go back to flat, and let's cut low frequencies, and now we can see small roll off here. So let's go back to flat, and let's try boosting high end, and there you go. Let's see, we have 10 dB per division, so we have let's say about 15 dB boost at high end. And let's go back to flat, and let's cut high frequencies, and now we have about 15 dB roll off. And again, it affects most of that region on the screen because this is a linear scale instead of a logarithmic scale. So this way is quick and easy, but not the best way. Now let's look at a special feature this oscilloscope has. Let's turn the FFT off and go to the analysis here. And in this menu we have frequency response analysis. And let's look at the setup. Here is a diagram. So we need to probe with channel 1 just before the input to device under test. And the channel 2 should probe the output. And the oscilloscope will measure the difference between input and output and plot gain for us and phase shift as well. So let's reconfigure our test setup like this. Now the second channel probe is connected to the dummy load. The generator is connected here. This goes to the input, and this goes to the first channel of the scope. Now we have a direct connection here on channel 1 instead of a 10:1 probe. So I changed the ratio here to 1:1. And now let's configure this frequency response analysis. Minimum frequency is 100 Hz by default. Let's change that to 10 Hz. Maximum is 20 MHz. Let's reduce that. We have a choice here between 10 kHz and 100 kHz. Let's go to 100. Amplitude 200 millivolts peak to peak. Let's reduce that to 100 millivolts to avoid clipping. Output load is high Z, and we should be ready to go. Let's turn the volume up to, let's say, 50%. Get out of this setup menu and run this. This will take a while, and now we have logarithmic scale here. Some sort of auto-ranging is happening, I believe. Now it is stepping through frequencies and measuring gain and phase shift. Here we are. Something strange happened to the phase shift around 100 kHz, and we don't really care about phase shift at the moment. Let's disable it here on the chart. And there you go. And now we should be able to explore this. Let's see, 20 Hz is right here, and we are at about 33.5 dB. And when we move through this range, we can see that we stay very close to 34 dB, plus minus a little, all the way up to here, let's say, which is 20 kilohertz. And we are still at around 33.5 dB. So the response is quite flat from 20 Hertz to 20 kilohertz within a dB or so. Now let's boost low frequencies and run this again. Here we are. Let's see. The peak of this boost is around 50 Hertz, and we see 47.7 dB. The baseline was around 34 or so. So we have about 13 or 14 dB boost. Now let's cut low frequencies and run this again. Here we are. Let's see, around 50 Hertz we have 21.8 dB. So let's see, we have about 12 dB or so drop. Now let's put this back to the middle and boost high frequencies and run this again. Here we are. Let's see what happened now. It started rising around this point, which is about 2 kilohertz, and the peak is around 15 kilohertz or so, 15 to 20 kilohertz, and the peak is about 44, let's say, dB, which is about 10 dB above that baseline. Looks great. Now let's cut high frequencies and run this again. Here we are. This time it gradually dropped from around here, which is 250 Hertz, and it started dropping steeper around here, which is about 2 kilohertz, and here let's see, around 15 to 20 kilohertz we measure about 24 dB, which is again about 10 dB different from the baseline. Looks great. So this is a much better way, and we still have that 8-bit front-end limitation, so this is not super precise, but for this purpose it is just fine. Now let's talk about some other ways. One more way would be to use a computer sound card. Plenty of resolution, at least 16 bits and maybe 24 bits, and a wide variety to choose from, starting from built-in and cheap to external USB professional recording interfaces. And software exists to do FFT transforms and all sorts of measurements. However, there is a problem with handling high voltages. We should expect, let's say, 100 volts peak to peak from amplifiers, or maybe even more, and that would be around 35 volts RMS. So some sort of buffering and scaling front end is needed that would limit the voltage to the input of the sound card, even if you choose a wrong range in that scaling buffer. And that buffer should be designed properly. It should not introduce extra distortions, and the frequency response should be flat, and so on. And there is also a problem with calibration. The software should be aware of the exact scaling factor to put any absolute numbers on the measurements. Otherwise, we can only look at shapes and do relative measurements. Yet another way would be to use a specialized audio analyzer. And wide variety exists again from different manufacturers: Audio Precision, Keysight, Roden Schwartz, Stanford Research, and some used gear on eBay, sometimes very old gear. And usually we are talking about thousands or even tens of thousands of dollars here. And now I want to show you yet another way. I have here this Agilent function generator and this 6.5 digit multimeter, plenty of resolution, effectively let's say around 20 bits or so, and it is very accurate and can easily measure up to 100 kilohertz, let's say. And here I have this GPIB to USB adapter, and I have this GPIB cable, so I can connect both instruments at the same time. This is a script in Python to step through the frequencies and measure the response. Let's briefly look at it. Here we define both instruments by name, and these names correspond to some addresses in the GPIB configuration file. This is the frequency range from 20 Hz to 20 kHz, 10 points per decade. Output voltage is 100 millivolts peak to peak. Here we import three libraries: GPIB, time for the sleep function, and math for logarithm and power functions. These are two helping functions to talk to the instruments. Here we initialize a function generator and print its ID. Here we initialize the multimeter and print its ID as well. This is to set a sine wave output of the desired voltage, and we print that voltage here. And here we start printing the results. This is the measurement loop, and a slightly tricky part here to organize stepping through decades, but not very difficult. Just a few lines of preparation here before the loop and a few lines here inside of the loop. And this line is to set the current frequency, and here we read voltage RMS from the multimeter, and here we print both with a tab in between. Now let's run this with the volume knob set to the middle as before. Now we can save these results and plot them somehow. And by the way, these measurements can be done manually with no GPIB interface. If 10 points per decade is enough, not too many points here, so this can easily be done manually. Not that convenient, of course. And the plotting can be done in many different ways as well. One way would be to use Python again. Another way is to put this into a spreadsheet and plot from there. It can be Microsoft Excel or open source equivalent or Google Doc or something like that. And I am going to use another way which I am familiar with, and that is using MATLAB, or to be specific, its open source equivalent called Octave. And here it is with a tiny script again, just to have a repeatable process, to tweak some details like font size, labels and such. And here I convert voltage RMS to dBV, which is a logarithmic unit relative to 1 volt RMS. And I'm using semi-log plot here with logarithmic scale on X but linear on Y, because we have logarithmic units there already, so this works fine. And here is the result. And I run the measurements again with 100 points per decade this time, to have more resolution on the x-axis. And we have a lot of resolution on the y-axis as well, because the meter is so accurate. And this is the flat response. Does not look very flat, does it? But this is because we are looking at the range from 10 dB to 9 dB. So let's say this is a zoomed in version of the plot. And by the way, when we move this cursor, we can see coordinates here in the corner. So this point, let's say, is 20 kilohertz and about 9.1 dB. So in fact, this is quite flat, within 1 dB from 20 Hz to 20 kilohertz. And here is another script, plotting 3 lines at the same time, flat, low boost and low cut. And here is the result. This time this flat response looks quite flat because of the different scale. And again we can see coordinates here, so here we are at about 19 dB, and this is 10 dB, so about 9 dB boost. And here we are at negative 2.5, let's say, dB. So again about 12 dB cut here, which is very close to what we measured with the oscilloscope, but this time it is much more accurate. And finally, flat, high boost and high cut. Here it is. Let's see, this point is about 16.5 dB, and this point is about 9. So we have about 7.5 dB boost at 20 kilohertz, and this point is almost 0, so about 9 dB cut at 20 kilohertz. There you go, so many ways to measure and plot. Please feel free to discuss this below or on the EV blog forum. I will put a link into the description. Thank you very much for watching. Bye.